So next is Shapiro's lemma. So this is one of the basic results in group cohomology, and it basically relates the cohomology of group G to that of its subgroup. But before we go into that, let's just see some general things. Suppose R and S are associative unital rings, and F is a ring homomorphism from R to S. Then if you have any left S module, say N, then can also be thought of as a left R module. There's a natural structure R dot N. You define it to be just using this F of R dot N. And N with this R module structure is said to be obtained via restriction of scalars. We are restricting the scalars from S to R. This actually gives a functor from like S mod to R mod. It's like a forgetful functor. And in this way, even the ring S can be thought of as a left R module. Now, this is from S mod to R mod. What about from, can we go from R mod to S mod? So that also we can do. Suppose we have a left R module, let's say M. Then there are two different ways. First of all, let's consider this S tensor M over R. Then for this to make sense, S has to be a right R module and left S module. Then this overall becomes a left S module. So this is called the induced module, induced by M. And so for this, S has to be a SR bimodule, which is there, which is already there. They are compatible, the S and R module structure on S. And similarly, you can also talk about this Hom S comma M over the ring R. Now here, S is considered as a left R module. M is also left R module, but it also has a right S module structure. So this becomes a left S module, and this is called the co-induced module. So S is here RS bimodule. In any case, M is said to be obtained by extension of scalars when you go from the R mod to S mod. So these gives us functors, the co-induced and induced functors from R mod to S mod. So what is the relationship between these two functors? The thing is that the induced functor, induced module functor is left adjoint to this restriction of scalars functor, F hash, and the co-induced is right adjoint. So this is actually pretty easy to see. This follows from the tensor Hom adjunction almost immediately. So you see that this induced functor, which is this S tensored dash, this is a left adjoint via the tensor Hom adjunction to which functor? To this functor Hom S S comma dash. Now this is a functor from S mod to R mod. If you take any S module N and you apply this functor, you get Hom S S comma N. Obviously this is isomorphic to N, right? As a abelian group, it is isomorphic, but also notice that this uh, uh, also isomorphic is S module, but also because this Hom set has a structure of an R module, left R module, and N also has a structure of left R module. This is in fact isomorphic as left R modules. Alright, so this essentially is a restricted version of N, considered as a left R module. So that tells you that this functor Hom S S dash is isomorphic to F hash, this restriction of scalars functor, and because the adjoints are unique, this has a this has a left adjoint this tensor product. Therefore, this must be the same. So that proves the first half. For the second half, it's almost the same thing. Here, what by the tensor Hom adjunction, you see that what is the right adjoint to this? Uh, what is this left adjoint to this Hom S comma dash functor? By the tensor Hom adjunction, you see this is this S tensor S dash. Now this functor again from S mod to R mod. If I take any S module N, then S tensor N is nothing, is isomorphic to N as a left R module. So this functor is also another way of expressing this restriction of scalars functor. All the things, I mean, in any way, difference here that S is considered the left R module or right R module in this case and the previous case, Hom case. So this tells us that this functor F hash is naturally isomorphic to this, but we know that this is left adjoint to this Hom functor, therefore this is also left adjoint. So that proves the proposition. Now let's go to the actual Shapiro's lemma. So suppose I have a group G and a subgroup H of G, then obviously this induces a map from the group ring ZH to the group ring ZG. Now if A is a left H module, which means a module over this ring, then by extension of scalars, I have two different flavors of that. I can transform into a module over ZG, that is a G module. One is the induced G module, known as the induced G module, whereby you take ZG tensored M over ZH, and one is the co-induced G module, whereby you take similar thing, Hom ZG comma A over H. Okay, So what the Shapiro's lemma actually says, the statement is that if you look at the homology of G, how do we relate the homology of G to the homology of A? If we have a if A is a H module, a left H module, and the nth homology of H in A is the same as the nth homology of G in the induced module of A. I mean, you have to take a G module here, and here you take the induced module for the homology. And dual version is that the nth cohomology of H in A is the same as the nth homology of G in the co-induced module of A. So here you take the co-induced module for cohomology. So okay, let's try to prove this. So the idea is that notice that this ZG is a ZG module, but it's also a ZH module, right? And it's actually a free ZH module. Why? Because if you take any set of coset representatives of H and G, let X be any set of such coset representatives, then they will generate ZG as a ZH module. That's easy to see. Because any G, you can write it as some G prime times H, so that H gets an element of ZH, so that is the scalars in this case, and G is your coset representative. So the point is that since ZG is a free ZH module, if I take any projective ZG module, say P is a projective ZG module, then P is a direct summand of some copies, some direct sum of ZG, some direct sum of ZG. But since ZG is a projective ZH module, direct sum of ZG is also a projective ZH module, and therefore that direct sum is also a direct summand of a free ZH module. So it's like some direct sum of ZH. Therefore, the original ZG module P is a direct summand of some copies of ZH, a free ZH module. Hence, P is a projective ZH module. So that is the restriction of scalars essentially takes a projective module to a projective module in this case. So therefore, if we start with a projective resolution of Z as right ZG modules, let's say P is a projective resolution, then if you think of them as just ZH modules, then they are also projective, but the sequence will still remain exact, right? So this is also a projective ZH module resolution. Now, with this, what happens is that how will you compute this homology? You will take this projective resolution P as ZG modules and take the tensor with the induced module P tensor ZG over induced, but this is nothing but P tensor ZG tensor ZA. I mean, this is P, yeah, so this is now by the property of tensor block, this is P tensor ZG tensored with A. Now P tensor ZG over ZG, mind you, is isomorphic to P as a ZH module. So this is nothing but P tensored A over ZH, which if you evaluate, so this as chain complex is isomorphic to this chain complex, and the homology of this is the group homology of G, and the homology of this one is this homology. So therefore these are isomorphic. Similarly, I can work with the opposite way, like I can talk about a left ZG model resolution of Z, and here also I have some kind of relation between the Hom sets. So if I take so how to compute this cohomology of G with coefficient in the co-induced module, I will look at the Hom G P comma co-induced A, right? This is nothing but Hom G P comma Hom ZG A by definition. But now you realize that this co-induced functor is a right adjoint to the restriction functor. Okay, so this by the defining property right adjoint, this is isomorphic to Hom H P comma A, where P is now applied. P is restricted to being a ZH module. So this is isomorphic as co-chain complexes, and therefore the cohomology of this, which is this, is the same as the cohomology of this, which is this, because P is a projective ZH resolution as well. So the cohomology will be computed by taking this cohomology of this co-chain complex, and that's the proof. Now, a special case is that when H is a trivial subgroup. Now, if H is a trivial subgroup, if you apply this theorem, if H is trivial, then the homologies they have nice, right? The homologies and cohomology are the same, and the zeroth one is A, and all higher ones are 0. We have seen that before for a trivial group. So that tells you that the nth homology of G of this co-induced model, which is right ZG tensor A. Now here ZH is nothing but Z, so this becomes Z, and here also H and G Hom over Z, ZGA. This is nothing but A if n is 0 and 0 if n is bigger than 0 for any H module which is an abelian group, so any abelian group A. Okay, fine. Now, if the index of the group, index of H and G is finite, that means this ZG is finitely generated as a ZS module, then these two different ways of extending scalars, co-induced and induced G modules, are the same. Why? Because the ZG is a finite direct sum of ZH. Then I can rewrite this tensor product and I can take the direct sum out to get this thing which is nothing but A, so I get direct sum of n copies of A. Then similarly, if I take the Hom with this ZG and A, then ZG is direct sum, but when I take the direct sum out, I normally get a direct product. So I'll get the direct product. But this thing obviously is A, isomorphic to A. So this is the direct product of n copies of A. But now since the direct product is taken over a finite set, it's the same as the direct sum. So this is isomorphic to this. Therefore, the induced and co-induced models in this case are isomorphic. Functors are the same. So these observations give this corollary that if G is a finite group, then apply this thing that it's a finite group, therefore this index will be finite. I mean, put H equal to 1, then this index is a cardinality of G which is finite, right? So then the co-induce and induce are the same. So what is this nth cohomology of G? So you apply this case with H equal to 1, nth cohomology of G with Hom, this thing, Hom Z, ZGA. This is equal to 0 if n is bigger than 0 and A if n equal to 0. But since this is now the co-induced module which is the isomorphic of the induced module, I can write this in place of this. So I get nth cohomology of G with coefficient ZG tensored A is 0 for n greater than 0 and any abelian group A. And this gives the original thing that we said a few slides earlier, that if you take now A equal to Z, then ZG tensored Z is over Z is just ZG. That tells you the higher cohomologies of G with coefficient ZG vanishes. That's something which we said earlier. So now is the proof. As another application of Shapiro's lemma, we look at the famous theorem, Hilbert's theorem 90. Now, this theorem was, or actually people see this theorem in some way or the other in a course on Galois theory, but there are usually two versions, one is the additive version, another is the multiplicative version. So, but the actual statement is cohomological or homological. So let's try to see. So what this says is that, remember we talked about this G module L. If you have a Galois extension L over K, this L and L star both are G modules. Example we have talked about. So it tells you about this homology. So if L over K is a finite Galois extension, with G being the Galois group, then the nth homology and cohomology, higher ones, they vanish with coefficients in L. This is the statement. So let's try to prove this. Now notice that L is not only a G module, it's a G representation, because it's also a vector space over K, and the G action preserves this scalar multiplication of K as well, by the field elements as well. So that means it's a G representation, that is, it's a left KG module. It's not only a ZG, it's a KG module. Okay. Now there is so-called normal basis theorem, which asserts that a finite Galois extension always has a normal basis. What is the normal basis? It's the normal basis is a basis which is given by the Galois basis of the vector space L over K, which is given by all the Galois conjugates of a particular element in L. So by the normal basis theorem, something which is there in a course on Galois theory, that there exists an alpha in L such that all the Galois conjugates of alpha, G alpha, they generate L. They are a basis of L as a K vector space. Thus what happens is that if you think about this map from KG to L, which sends 1 to alpha, this is enough to give a KG linear map from KG to L. Since the Galois conjugates of 1 in Kg, which are the group elements, they form a basis of Kg over K. Similarly, and since their images now, which are the Galois conjugates of alpha, they form a basis of L over K. This tells you that this map is an isomorphism of K vector spaces, but also it's once it's an isomorphism of K vector spaces, it's also an isomorphism of Kg modules. That is easy to see. Hence, as Kg modules, L is isomorphic to Kg. Another way of saying this is that L is actually a regular G representation. Okay. So note that kg is nothing but isomorphic to zg tensored with k. Here zg you consider as a left zg module and right z module, k as a left z module, right k module. So this becomes a zg k bimodule, but you can give it a structure of a kg module. But the point is that as zg module itself, you have this isomorphism because this is isomorphic to kg, which is isomorphic to this. Okay, so now it looks in the form that you want. Now you can apply Shapiro's lemma, this corollary, that G is finite, yes it is. Now you apply Shapiro's lemma to conclude that. Now this, remember, holds for homology as well as cohomology, right? So cohomology of G and L, because L is this, is 0. Same with homology. So that's for n bigger than 0. So that's the proof. Now usually people see it in this version where you take G to be a cyclic group. That means you take more cyclic extensions. Suppose that's the case, G is cyclic generated by sigma, then you can convert this result, at least for the first cohomology. You can, because we know, at least essentially we have tried to describe homology and cohomology groups of cyclic groups earlier. So then this can essentially turns out to be the statement that if you take any element in L such that this trace, whose trace function evaluated on x is 0, then there has to be a such that x is sigma a minus a. So that's an unpacking of this statement for cyclic extensions. Okay, later we'll see a multiplicative version as well. So now let's talk about this bar resolution. So what is this? Basically, you want to compute homology groups and cohomology groups, it suffices to give a projective Z resolution. So now we're going to describe a very standard Z resolution of particular projective resolution of the Z as ZG modules, which will help us in computing the homology and cohomology groups. It's a very expressive resolution. So how do we describe this? So suppose Fn is a free Z module generated by all n plus 1 tuples of elements of G. So elements of the form G0, G1, Gn, n plus 1 tuples. So it's the free abelian group generated by these tuples. Then I have to make, this is a abelian group, I have to make it to a G module. So I have defined action by G. So take an element G, I define G dot this element, basis element, I define it to be the obvious way, G, G, G naught, G, G1 and so on. So so this becomes a G module or a ZG module, and now it's also a free ZG module, because if I take any element as a Z basis, if I take G0, G1, Gn, I can take G0 out and write it as G0 by this action G0 dot 1 G0 inverse G1 whatever, so on. So basically this tells you this set 1 comma G1, G2, Gn, Gi's and G, they generate this as a ZG module. So this is a free ZG module. Alright, so we have this collection of free ZG modules Fn indexed by non-negative integers, and we want somehow, so this is a projective resolution. For that we need to give some differentials, differential maps. So we define these differential maps as follows. From Fn to Fn minus 1, I take the basis element G0 to G1, Gn, and I send it to this summation I equal to 0 to n minus 1 to the power I. What this element, what is this thing? You basically take this n plus 1 tuple and remove the ith tuple or the ith component Gi. This hat denotes that it's removed. So this becomes an n tuple element of Fn minus 1. So this is the map. Now these maps, you can extend these maps linearly obviously, and this map is a abelian group map, but also it's a map between ZG modules. That's easy to check. Then what about the map from the last map in the, like from F0 to Z, there should be a map, right? Now F0, notice, is nothing but ZG. It's a free Z module generated by G. So ZG. So that map from ZG to Z is there. That's the epsilon. That's the augmentation map. We put that there. Okay. So this becomes, we have to show it's a chain complex at this point. But so we claim that in fact this is a free resolution of Z. To show it's a free resolution, we have shown that these are free ZG models. All we need to show is that they form a chain complex. So D composed with D is 0 and it's exact. So let's just first show that it's decomposed with D is 0. Suppose I take I look at first this map from F0 to so this map from F1 to F0 followed by the epsilon map to Z. I take any arbitrary basis element G0, G1 in F1. Then if I apply D1, by this definition, I'll get G1 minus G0. Then I apply epsilon, I get 1 minus 1 which is 0. So that is fine. For the other maps, I also claim that their composition is 0. So that is, if I take any basis element in Fn, like this, apply dn minus dn and then dn minus 1, I get this summation. So what they're doing, I get this thing, right? So what basically they're doing is that they first we are removing gi and gj, right? Removing two elements. I have to remove two elements from I and j. Which I and j? You look at all I and j possible. So first remove the j from any j from I 0 to n, and then from any I from 0 to n minus 1. So note that this summation is 0. Why? Because if you fix an I, so suppose fix ij, I less than j from 0 to n, then suppose you first remove j. Okay, so when you remove j, you get a factor of minus 1 to the power j, but then you also remove I, so then you get a minus factor of minus 1 to the power I. But then you remove I and j, and that's gone. So you get a minus 1 to the I plus j factor. But then suppose you remove I first, right? If you remove I first, you get a factor of minus 1 to the power I, but now you have to remove j second. J next you have to remove. The thing is that j is now shifted because this is moved, so this goes in the left. So now you have to actually remove the j minus 1. So to remove the j, you have to remove the j minus 1 tuple or index here, uh, coordinate. So you get a factor of minus 1 to the power j minus 1. So overall you get a factor of minus 1 to the power I plus j minus 1 with the same n minus 1 tuple here. So because of these two different signs, it gets cancelled and the sum is 0. So this tells you that this complex is actually chain complex. Now the next thing to show is an exact chain complex. So for that, we will show that it is a split exact chain complex. That is, it is the identity map on this chain complex is null homotopic. So for that we need to define these maps which go in the opposite direction. So we define these maps Sn from Fn to Fn plus 1, which takes a basis element G0 to Gn and sends it to this one G0 Gn. And extend these maps Z linearly. Notice that Sn is of course a Z linear map, but it's not a Zg linear map. It's not preserved by action of G, but it's a Z linear map. And we view this chain complex as a chain complex of Z modules because these maps that we are getting, they are only Z linear. So we view them as Z modules, and now of course you have to define the map from Z to F0, this map from Z to F0, that are defined by taking the identity 1 to 1. S minus 1 I define 1 to 1, and of course there are zeros in the right here, and those maps of course from 0 to Z, from 0 to 0, these maps are called 0. So I define Sn to be 0 for all n less than minus 1, and then you compute this dn, this ds plus sd combination, you compute for any arbitrary basis element. It is easy to see that this turns out to be equal to just g0 to jn, so the same. So these maps is identity, at least in this half. Now here also this is the case, because if you take here one, so this map is 0 if it doesn't count, so you take the 1 to 1 and then you get back 1, so effectively this is also identity, and everything this works out, right? So this explains that this is a split exact chain complex and over Z modules, and hence it's exact, right? So that's what we wanted to prove. This completes the proof. So this is a ZG resolution, free ZG resolution of Z. Now we change some notation a bit. So we introduce this new notation with this square brackets and these bars. We have this symbol G1 to Jn. We define it to be like this n plus 1 tuple, 1 G1, G1, G2 and so on. Of course we can interconvert. Given this n plus 1 tuple, this becomes in this, under this definition, just equal to this guy. Now of course with this, Fn is a free Zg module. Since Fn is generated by, these are the basis elements of Fn as a Zg module. Under these symbols, this is a G model with basis given by these guys. I mean, this is an n tuple of G, right? So this is isomorphic to G to the n as a set. Of course, F0 in this case has basis given by this empty symbol. There's nothing here, but that's fine because F0 is Zg itself. It's only one element to generate as Zg module, which is this empty symbol in this case. Now under this notation, you can also see what happens with this differential. So differentials map, you can check that this differential of this thing symbol happens to be this thing. I mean, that's, you can easily check. Because of this lot of bars in this notation, we call this resolution a bar resolution. Now let's try to use this resolution to compute some cohomology groups. So we define CNGA to be the set maps from G to the n, all functions essentially from G to the n tuple G to A. Of course, this is a structure of an abelian group. Why? Because A is an abelian group. I mean, A is a G module. So notice now that since Fn is a free abelian group generated on this set of symbols, which is isomorphic to G to the n, the all G module maps from Fn to A are an isomorphism with all set maps from G to the n to A. Right? I mean, this direction is given by restricting this map to G to the n, and in another direction, if you have a map from the bases essentially, then you can extend it ZG linearly to get a map from Fn. So these are isomorphic as abelian groups under this map. Under this isomorphism, I can also define the differentials for this cochain complex. Of course, this is a cochain complex, right? Because this is isomorphic to a cochain complex. So I can define this map from Cn minus 1 to Cn. And you can again check this definition comes from the definition of differentials on this Hom cochain complex. This is the definition, right? So F, an element here, a set map from G to the n minus 1 to A, goes to a set map from G to the n to A, which is this thing. So so these elements in this cochain complex CNGA are called n cochains, some terminology. The kernel of this map is kernels of this chain complex are like ZNGA. These elements are called n cocycles, and the images of these cochain complexes, they are called denoted by B to the n GA, and the elements are called n coboundaries. Okay, that's some terminology. And then it's easy to see that in the cohomology groups, since the cochain complex of Cn is isomorphic to the cochain complex of homology and A, which is used, and the nth cohomology of this will give you, and the cohomology groups of this cochain complex will give you the group cohomology. So therefore, group cohomology is just the n cocycles modulo the n coboundaries. So with this simple description, relatively simple, we can compute lower cohomologies. So let's try to do that. So what about the first cohomology? So here we have to understand what are one cocycles and one coboundaries. And the one cocycles modulo one coboundaries will give you the homology. Now one cocycle means it's a function, a set map from G to A, just one copy of G. Now if you look at this definition, right, then it is easy to see that it will be a one cocycle if f of G1 G2 is G1 dot FG2 plus FG1. This is the so-called one cocycle identity. And again by this definition, a set map from G to A will be a one coboundary if it is of the form f of G is of the form G dot A minus A for some A in A. Again, these are just follows easy from these definitions. Then from this information you can say that for a trivial module A, the first cohomology is nothing but the group homomorphisms from G to A. Why? Let's look at one cocycles here. So the one cocycle condition here, notice that since A is a trivial G module here, this G1 dot f of G2 is an element of A. G1 action is just trivial, so this is just f of G2. So f of G1 G2 is nothing but f of G1 plus f of G2. So this is just like a homomorphism, so groups. So the Z1, all the cocycles is nothing but all group homomorphisms from G to A. And what about the coboundaries? Since again the action is trivial, any element in the coboundary, since G dot A is A, so this is A minus A0, any element will be 0. There is no non-trivial coboundary. So again the coboundary is 0, so the homology is just the group maps from G to A, group homomorphisms. So this immediately tells you that, for example, if you have a finite group G, you want to compute the first cohomology of G with coefficient Z, that's nothing but the group morphisms from G to Z. Now if G is finite, this is 0. There are no non-trivial morphisms because Z is torsion free essentially. So again, using this we can prove this result, which is helpful. I mean, I'm not going to give a proof here. You can see the book by Charles Weibull on Introduction to Homological Algebra for the proof. So what it says is that if you have a finite group with size M, then if you take any G module A, then the higher homology and cohomology groups, that is for n bigger than 0, they are annihilated by m times that is 0. So this is helpful also, I mean, in some computations. Okay, so let's look at another application, which is to prove the Hilbert's theorem 90. Now in the multiplicative version, that is, now we are talking about the group action of the Galois group on L star, on the multiplicative group, not on L. So again, the statement is that the first cohomology group vanishes, right? Only the first one I'm saying. So let's try to see why. So if I take, what I have to show is that any one cocycle will be, any non-zero one cocycle I can take. Suppose F is a non-zero one cocycle of G, so map from G to L star. I have to show it's a one coboundary, then I'm through. Okay, so if it's a one cocycle, what means that F of G1, G2 is, under the multiplicative notation, G1 of F of G2 into F of G1. Now, a simple fact from field theory says that if you have any field and take distinct automorphisms of the field, then they are linearly independent as functions over L. That means, notice that here G, the members of the Galois group, they are distinct automorphisms of L, different elements here. So therefore, by this fact, there exists an alpha such that summation G in G, F of G, G alpha is non-zero. Because F is assumed to be non-zero, so not all coefficients will be zero. So it's a non-trivial linear combination, and it has to be non-zero. So therefore, there has to be some alpha where it is non-zero. So let's call that element B. Now, take any arbitrary G prime in G, and let's see what happens if G prime acts on B. So G prime of B is, you go take this G prime inside in the summation, G prime of F of G, it's a ring map, G prime G alpha, whatever. And now notice that this G prime F of G looks like G1 F of G2. And by the fact it's a cocycle, I can write it as F G prime G upon F G prime times this thing. Of course, F G prime is independent of the summation. This is a summation, there is a summation here, summation G in G. Of course, uh, this G prime is independent of the summation, so I can take it out. Summation G in G, this thing. Now, this numerator is the same. I mean, the summation is running over G prime G instead of G, but that's the same set. So this is just the summation G in G of this thing, which is nothing but B. So what you get is that G prime B is nothing but B upon F of G prime. Now notice that B is non-zero field element, hence it has an inverse. So just rewriting this equation, I can get that F of G prime is G prime of B inverse upon B inverse. It will be B upon G prime of B, but in terms of B inverse it will be this. So that tells you that F is a co-boundary, right? Because under the multiplicative notation, F is a co-boundary if F of any group element is that group element times some element upon some element, that same element, right? So this is true for any G prime, remember. G prime was arbitrary. So this is a one co-boundary which finishes the proof. Co-cycles and co-boundaries are the same. Cohomology is trivial. Notice I'm not claiming that the higher cohomologies vanish, and in fact it's not true. For example, if I say, take the simplest possible case of the extension C over R, it's a cyclic extension, the Galois group is Z mod 2Z. Now just using the computations of cyclic groups cohomologies, you can compute the cohomology of Z mod 2Z with coefficients in C star, and it's the isomorphic to Z mod 2Z. So it's not zero, right? Now, the familiar version people usually see again in a course in Galois theory is the following, which again follows from this version, is that if you take any element x in L such that whose norm L over k of x is 1, then there has to be an A in case that x is sigma A upon A. Similar to the additive version, only thing is that you just write everything multiplicatively. So in place of trace you have norms and so on. Okay, so now RG modules. Now basically the point is that starting from the definition of G modules, we have been focusing only on Z, right? I mean, we're talking about G module as an abelian group with G actions, so it's a ZG module. But we can, and talking about these functors from ZG modules to abelian groups, these derived functors, the homology and cohomology. Now, you can obviously try to work with any commutative ring R instead of Z, and everything will work out fine. I mean, you can consider the category RG mod, right? Group ring over R, in which basically the R modules and G acts are linearly on those modules. Similar way, you have these functors, the invariants and co-invariants functor from RG mod to R mod, and they are all having these same properties, right and left and join, and you can form the derived functors, which are tor RG and ext RG, right? So these will be the corresponding homology and cohomology in that sense. But also, since any RG module is also a ZG module, we can also talk about its usual cohomology and homology, which is tor ZG and tor ext ZG. The thing is, they are the same. You do not get anything new when you do this thing. That is, if you take any RG module, then the tor ZG ZA is isomorphic to tor RG RA, and X ZG ZA is isomorphic to X RG RA as abelian groups. So this is the homology with coefficients in A, and this is the homology if you think everything in terms of the commutative ring R. The thing is that they're same, as abelian groups are same. So let's try to see a proof. Now here you use a bar resolution. So let's take F to be a bar resolution or the bar resolution, and here the thing is that Fn is a free ZG model, that's okay. So if I tensor this with R, tensored over Z with R, then there's a free RG module because ZG tensor R is RG, so it's a free RG module. And of course, if I tensor Z with R over Z, I'm going to get R. So Fn tensored over R, it's a chain complex you get with R as the right hand side in the 0th degree or whatever. So since this, now the point is that this F was acyclic, I mean exact, but it was split exact. It was more as complexes of abelian groups. It was split exact, and if you have any additive functor applied on a split exact chain complex, then it will also remain split exact. The reason, because a split exact chain complex is just given by this equation st plus ts equal to 1. When you apply any additive functor, it will still have the same property, f of s f of d plus f of d f of s is 1. So this suggests that if you apply any additive functor, you get this thing, but you have to be sure that you're working over z module. So I take this additive functor tensor z. This is an additive functor with z modules as an input. So if I apply the additive functor on f, this will still remain split exact. So f tensor zr, this chain complex, this entire chain complex is also split exact. This, and already they are free RG modules, so this explains that this is in fact a free resolution of R as RG modules. And I can use this resolution to compute this tor and X. Now it's almost finished. If I take any, how to compute this tor group, I will take this chain complex, I will tensor this with A. So I take this F tensors R over Z, tensor this with A over RG. But notice that this is isomorphic to F tensor R over ZG, because actually this bracket thing is isomorphic to F tensor RG over ZG, and hence you can get this thing. Similarly, the way to compute this, you take Hom of this chain complex F tensor R comma A, and again this is isomorphic to Hom ZG F comma A. So so of course this cohomology of this computes this X group, cohomology of this computes this thing. Similarly here, so that completes the proof. So okay, now earlier we have seen how this homology and cohomology is a functor. They are functors from G mod 2 abelian groups, and so now what we're trying to show is that actually they are functors in some sense of G as well. If we change G, then there is some kind of functorial relationship. So for that, let's suppose I take two groups G and G prime and a morphism from G prime to G. Then obviously I can have this restriction of scalars, this forgetful functor from ZG mod to ZG prime mod, and it's obviously exact. We have seen that earlier. Then if you consider these two functors, which is taking this exact functor, forgetful functor, and precomposing this by this homology of G prime functor, and similarly I can take this functor and compose with the cohomology. These are delta functors. Why? From G mod to abelian groups. So of course this is a functor from G mod to G prime mod, and this is a G prime mod to abelian groups. Why is this a delta functor? Because this is exact. I mean, essentially you need to take any exact sequence in G mod and apply this functor f hash. I still get an exact sequence, and then apply this. These guys are delta functors, so I can apply them, and then because of that I'll get a long exact sequence with boundary map. So therefore this S star and S star, these are all delta functors. Now notice that if I take the 0th guy here, the 0th one, which is the 0th homology composed with this. Now 0th homology is this functor h0 g prime. So this one, this h0 g prime dash compose f hash. Now if I take any object A, what I get is f hash A, and then look at the 0th homology, which is the co-invariance. So there's an obvious map from this thing to AG, very natural map. And Similarly, I have a very natural map from the invariance of A in G to take A, take the forgettable functor, and then take the co-invariance, invariance. So then this is also a natural map. So that means that between this functor S0 and this original homology functor of G, the zeroth one, there is a natural transformation. Right? This gives rise to a natural transformation. These natural maps, and this natural map gives rise to natural transformation from the cohomology of G to this composition S0, the cohomology G prime composed with F hash. So okay, so now notice that these, of course, these homology and cohomology of G are the universal delta functors of G mod 2 ab, and these S, they are delta functors, just delta functors whose zeroth functors, they have a natural transformation. Just by the definition of a universal delta functor, we know that these natural transformation in the homological case from S0 to this zeroth homology, this extends to a unique morphism of delta functors. Similarly, this morphism here, or this natural transformation between these two functors, extends to a unique morphism of delta functors. That's the definition of delta functors, universal delta functors. So it extends uniquely to a morphism of delta functors, which when you plug in A, you get a morphism of abelian groups, and these are what I call the co-restriction and restriction. So with the homology, I call them the co-restriction G prime. I get a map from the homology of G prime of F hash A to homology GA, and cohomology GA to cohomology G prime F hash. These are the co-restriction, and this in some sense does is a functor. I mean, because a map from G prime to G induces a map between their homologies and cohomologies. More precisely, I can say in a very precise sense why, how, and from which category it's a functor. So suppose you take the category C, define a category to have objects as the pairs G comma A, which are essentially the inputs of the homology and cohomology functors, where G is a group and A is a G module. And I define a morphism between two such objects, G comma A to G prime comma B is a morphism is defined to be a morphism from G prime to G, opposite direction, G prime to G, and it's a group homomorphism G prime to G, and a map from F hash A. So A is a G module. I can restrict it to get a G prime module from this to B. And since it's a map of G prime modules, I want this to be a G prime module homomorphism. So this is how I define it to be. This is how I define the morphisms in this category, and you can check it's a category. And then notice that because of this restriction map from the cohomology, I have a map from G to G prime to G. This gives me a map from H star GA to H star G prime F hash A. But then since there's already a map from F hash A to B, which is H, the normal functoriality will give you a map from H star G prime F hash A to H star G prime B. Compose these to get this map from H star GA to H star G prime B. And so you can check now this is actually a functor from this category C to abelian groups. So this is now what is homology, cohomology, cross, and cup product? So the point is that there is a natural product on this cohomology which turns it into a ring. It's not a usual ring, but we'll see. So first, some general observation. Suppose R is any associative unital ring, and if I have any two co-chain complexes, right and left R modules, there's a natural map from P tensor QQ to this sum, direct sum, the natural inclusion. This induces a map between the homology Pth homology of P tensor to the Qth homology of Q to the P plus Qth homology of P tensor Q. And this is the tensor product of these co-chain complexes. This is also a co-chain complex. Why? I mean, how is this map there? I mean, you can check that. Take any x bar, essentially the natural map. X bar tensor y bar goes to x tensor y bar. I have to check it's well defined and so on, but that's easy. Okay, so that's this observation. Just let it be there. Now, if I have two groups G and H, so the first idea is to somehow relate the homology slash cohomology of G and H with that of G direct product H, G times H. So what is this group ring first of all? G, Z, G cross H. What is this group ring? Notice that if I have, there's a map from ZG tensor ZH over Z to this group ring, whereby I send an element G tensor H to G comma H. I mean, this is a natural thing to do. First of all, it's a well-defined map, but this is also a ring isomorphism. Under the ring structure, natural ring structure is there on this tensor product. I mean, you can take G comma h times g tensor h times g prime tensor h prime equal to g prime tensor h prime. A natural structure you can give to a ring, and under this is an isomorphism of rings. So therefore I can think of this ring as this tensor product. Now suppose I start with a P is suppose a ZG resolution, free ZG resolution of Z, and Q is a free ZH resolution of Z. Then I take this P tensor Q over Z. This is a chain complex of, this is a ZG module, this is a ZH module. So this is a considering as a left ZG module, as a right ZH module. This is a ZH ZG ZH bimodule, and so with that also you can also give it a it's also a module over ZG tensor ZH, which is isomorphic to this. So this is a module over this ring. Now you can notice that this P is a free resolution, um, but as abelian groups is a free Z modules, right? It's a free ZG resolution, but it's also a free Z module. So applying the Kanath formula for chain complexes for this tensor product P tensor Q, I have this, the nth homology is this direct sum of this individual homologies tensored plus with this tall correction factor. So here this HPP tensor HQQ. Now notice that since P and Q are exact in this resolution, so these vanish if P is bigger than 0 and Q is bigger than 0. So if you want to compute this homology, if n is bigger than 0, notice that one of these must always vanish, so this is 0 anyway. This will vanish provided n is bigger than 1, and if n is 1, then this P and Q must be 0. So this is the 0th homology and the 0th homology, but the 0th homology of P is Z and the 0th homology of Q is also Z, so this is dot ZZ, which is 0. So eventually this is 0, so that means for any n bigger than 0, this homology is 0. So that tells you that this is actually a acyclic chain complex, or this is a resolution of Z as a free ZH, free ZG times H modules. So I can use this resolution to compute the homology and cohomology. Okay, so this is something. Now okay, so let's do something else independently. So I have this map mu. I can define this map mu from this is an abelian group, right? Take a pth guy here, so hom g ppz tensored hom h qqz to hom g cross h pp tensor qqz. How do you define? Take any f here, take any f prime here, that is f tensor f prime, and define and send it to a map here, which I call mu of f tensor f prime, and this takes any element of pp tensor qq, let's say x tensor y, and it define it to be f of x times f prime of y. Now if I have to check that this is a map of abelian groups, and this map induces a map between this cochain complex hom gpz, this is a cochain complex tensor with this cochain complex hom hqz, and hom g cross h p tensor q. This is a cochain complex, sorry, this is a chain complex, but when you apply the hom you get a cochain complex. So then this map induces, you have to check this map induces a map between these cochain complexes. Now let's use this map and the above observation to get some new maps. So suppose now if you take this cochain complex as your P here, and this cochain complex as your Q under this observation, and I know that there's a natural map from the pth cohomology of this cochain complex tensor with the qth cohomology of this cochain complex to the P plus qth cohomology of the tensor product of these cochain complexes, just by the above observation. But this pth cohomology of this, since P is a free resolution of this, is nothing but the group cohomology. This is nothing but the group cohomology. So now this thing hom g, but we already know that hom p z tensor hom qz, there's a map from this to hom p cross p tensor qz over g cross h. So apply this mu map. So this of course map of cochain complexes induces a map between their cohomology. So apply that map to get a map to the p plus qth cohomology of this cochain complex. But remember, this the p plus qth cohomology will give you the group cohomology of g cross h, because this, mind you, is a free z g cross h resolution. So that's why you can compute the cohomology using this. So that if you compose all these maps, you get a map from the pth homology of cohomology of G tensor the qth cohomology of H to the p plus qth cohomology of G cross H. And this map is what we call the cross product. All right. Um, so it's this has nice properties in the sense that it is associative, and this map is independent of the free resolution you choose. You take any different free resolutions, this map is still the same. Now, one other nice thing that happens is that, now notice this map mu between co-chain complexes is not necessarily an isomorphism. There's no reason for it to be, but if you have this free resolution P whereby every module is also finitely generated, it's already free, and then this map becomes an isomorphism. Now, first of all, when can this happen? I mean, it will happen if G is finite. One case it can happen when G is finite, because either you can think of like this way: it's a bar resolution, and a bar resolution gives this thing. Bar resolution makes it into because G is finite, so every Fn will be a finitely generated module. Or you can also see that if G is finite, then this ring is Noetherian, so you can get a finitely generated free resolution. Anyway, so this map is an isomorphism. Why? Because you just take P as a write P as a direct sum of finite direct sum of ZG and take out at get a direct product. But this is the same as direct sum. Here you will still get a direct product. Here also you can do the same thing. You'll get a direct product, but eventually you will see that these are isomorphic, right? If one of them happens to be finitely generated, in this case P, let's say. Also, if P is finitely generated free ZG module, if I take this cochain complex, then this cochain complex is composed of all modules are free, finitely generated free Z modules, right? I mean, they are free, that's the point. So then I can apply the Kunath formula for these. Kunath formula for which cochain complexes? This Hom GP comma Z and Hom GQ comma Z. And the thing is that in the Kunath formula here I'll get the pth cohomology of Hom GPZ, which is nothing but the group homology. And similarly here also I get the group cohomology. I'll get all correction factors in the middle. However, I will get the p plus qth cohomology of the tensor product of these cochain complexes. But now, because of these are isomorphic to this, so I can just write hp plus q of this cochain complex, which is the group cohomology. So then the Kunath formula will give you that this sequence is split exact. So this helps you to figure out the cohomology of G cross H in terms of the cohomology of G and the cohomology of H. Now, similar formulas are also true for homology. In that case, there is even less restriction on P. In fact, there is no restriction. So the similar formula is also true for the homology. That's the point. Now, let's consider the special case when G is equal to H. Right. So now this cross product gives a map from the pth cohomology of G in Z tensor the qth cohomology of G in Z to the p plus qth cohomology of G cross G in Z. But now notice that there is a very natural map from G to G cross G, a group homomorphism, the diagonal map, which takes G to G comma G, and under this map, and using the functoriality of the cohomology, I get a restriction, this restriction map from the cohomology of G cross G to the cohomology of G. Yeah, I can restrict this. So this works with cohomology, or homology will work in the opposite direction, right? So I can compose these maps now to get a map from the pth homology cohomology of G tensor the qth homology of G to get a p plus qth cohomology of G. So this map is what we call a cup product. Now the cup product is nice. Why? Because it turns this cohomology into an associative, graded, commutative ring with unity. Now you may say, what is that? Now first of all, what is a graded ring? A graded ring is just a ring such that the underlying abelian group is a direct sum of abelian groups indexed by the natural numbers, say. So R0, direct sum R1, direct sum R2, and so on. Whereby the multiplication is such that, so each of the Ri's is the abelian group. Multiplication is such that Rj is contained in R of I plus j. That is, if I take an element in Ri, multiply with an element in Rj, I'll get back an element in Ri plus j. That's a graded ring. If it's associative, it's associative graded ring. Now, commutative is slightly different. Graded commutative means that if I take any element x in Ri in the grading and y in Rj, then xy is not equal to yx. I'm not saying that. What it says is that xy equal to minus 1 to the power ij times yx. So the degrees of where X and Y belong in Ri and Rj. They change whether it's commutative or anti-commutative. So this is called. So I mean, you can. I mean, this proof I'm not uh, mentioning the proof here. Proof is a bit long. A lot of verifications are there. You can look at the book by Charles Weible to for a proof. And so this uh, makes it into a ring. That's the point. I mean, not this basically, but the direct sum of all these cohomologies combined is a ring. That's the point. Maybe that's the reason why cohomology comes up a lot, because it has a ring structure. Homology is different. You might get a ring structure there. So anyway, that's the end of my presentation. Thank you.